Hello and welcome to part 8B of the talks on the glorious geology of Iceland for everyone. And in this part 8B, we drive in our imagination from Skógafoss, where we left off, and then to the famous beach of Reynisfjara, and then into the vicinity of the Katla volcano and its sandur plains. So, in part 8A, we reached to Skógafoss, marked here by E. So, in this part 8B, we drive simply along here and then to Reynisfjara. And from Reynisfjara, we see also Dyrhólaey located here. And then back from Reynisfjara and out into the sandur plains a little bit to look at Katla, or the Katla volcano, and the sandur plains and how they have formed. We also look at these mountains here and here, and we discuss their formation. But on the way, there are other structures like this little one here called Pétursey that we shall discuss. And let's now go for it. So here are the main sites that we discuss, shown a little bit better. So first of all, we will discuss this Pétursey. Then we go down to Reynisfjara, the Black Beach, and its cooling joints or columns, famous so, including caves and other things here. We take a little look from a distance at Dyrhólaey, located here. Then we drive back around this mountain here, Reynisfjara, and down to the little village of Vík. I will not discuss the village as such, but I will show you again the sea stacks that we can see from, first of all, from Reynisfjara and then from Vík that stand out here. And then we drive a little bit into the sandur plains and we discuss the mountains we see, this one here and that one, Hafursey and Hjörleifshöfði, and we discuss the sandur plains, how they're related to Katla, the Katla glacier, the Katla volcano itself, which is a collapse caldera, and located inside Mýrdalssandur, the ice cap of Mýrdalssandur. You see, in comparison with Eyjafjallajökull, Mýrdalssandur is much larger, and the floods that come from here during significant eruptions in Katla are enormous, absolutely enormous, and I will discuss them in some detail with you. So the first remarkable structure we look at on the way is Pétursey. Now, Pétursey is a hyaloclastite mountain. You see it very clearly here. We are looking here from road number 1 to the west. There's a farm here located under the mountain. Now, as I'll mention sometimes again to you, means in fact island. And the question is, was this an island during the settlement 1100 years ago? Quite possible that it was. It is definitely not an island today. It is in fact, the southern end of it is 3 kilometers from the coast. So the coast has been extending by around 3 meters per year, if this was initially an island or close to being an island during the settlement. And how could that be the case? Well, through accumulation of sediments. Where do these sediments come from? From the glacier rivers, the numerous glacier rivers in southern Iceland. And particularly, they come from the floods during eruptions. Now, the last major flood from the Katla was in 1918, and I will discuss that later. But here we see a much smaller one formed during eruption in 1996 inside the Vatnajökull ice sheet, the biggest ice sheet in Iceland. It was not very large, but you see here the meltwater, the muddy water coming down here from the glacier, far, far away. Here is the main coast, and you see the muddy water coming here into the Blue Sea, and this, of course, is carrying a lot of sediments, and gradually they extend the coast to the south. So now we are down on the beach, the famous Reynisfjara, and first we look to the west at the mountain or remnants of a mountain called Dyrhólaey. Now, this again is a hyaloclastite mountain, not very large. It has a beautiful hole inside it formed by, of course, sea erosion. And then you see some pillars or sea stacks extending from it. There is a separate road down to Dyrhólaey if you would like to go there yourself. But here we focus on Reynisfjara, where I'm standing when I take this photo. And so we turn now to the east and look at the main things we can see as regards structure of the Reynisfjara, the fjara itself, the beach itself is this one here, of course. And people need to be very careful there. There have been accidents there due to the waves, and so people have to be very careful there, please. But if you look at the mountain itself, it's called the Reynisfjall, a hyaloclastite mountain with the lava flows on the top. Here, the height of the mountain is only around 150 meters, but the highest part of it, further to the north, is around 340 meters. In fact, it's 5 kilometers long, north-south. And there are several interesting structures to look at here. First of all, there is a sill, it's a horizontal intrusion, basaltic intrusion here at the bottom, at the floor of the mountain. And then in addition is an inclined sheet here. They're meeting somewhere there. And then on the top, there are lava flows. And these lava flows are clearly fed by a dike, supplied with magma by a dike that is seen here, and I'll show you much better later on. And let's first zoom in or focus a little bit on the famous cooling or columnar joints that we see here in the lowermost part of the sill. They are strikingly beautiful, and all cooling joints or columnar joints are what we call joints. That is mostly pure opening, pure extension fractures. So there is no fracture parallel, wall parallel movement. They are not shear fractures. They are pure opening fractures. And they form because the magma here in the sill in this case, but it could be a dike or a lava flow, the magma cools down, and then when it cools down, it shrinks, like most liquids, not all, not water under certain conditions, but most liquids, when they solidify, the volume is reduced. And in this case, if you take a body like that, a magmatic body, then commonly, when it cools down completely to the surrounding temperature, the reduction in volume may be around 10%. 10%. And as a consequence, these joints, these cracks, these fractures form. So they initiate at the parts of the body, here the sill, that are the first ones to solidify. And which parts are those? Well, obviously the surface parts. And from these surface parts that cool initially, the joints propagate then down. So they propagate down here from the surface, which was higher up there. And they would also propagate from the bottom, but the cooling is often more rapid in the upper part. It depends, of course, on the circulation of groundwater and many other things. But that would imply that the propagation may be more rapid from the upper part and into the center of the body than from the lower part and up into the center of the body. However, please notice the cooling joints do not start to form as soon as the body solidifies. The body, this kind of body would solidify if it's basaltic body, say initially 1200 degrees. It becomes solidified at around 1000 degrees. But then still it's very, very hot. And the joints only start to form when it has cooled down to around 60% of its initial temperature, that is to say, around 700 degrees. So it takes a long time for the joints to form and start to form. So as a general rule, when there is a temperature difference between two parts of a body, or a body and its surroundings, like let's say here, where this was fluid, just emplaced, there was a temperature here of 1200 degrees, and then in the surrounding rock, maybe 100 degrees or something like that. Then obviously there is a gradient. There's a gradient. And the heat flow, the flow out of the body is always down the gradient. It applies, of course, to the Earth as a whole. The core of the Earth is much warmer than the surface, and there's a general flow of heat out of the Earth from the core. Of course, mainly the outer core, because the outer core is fluid, and through the mantle and then through the lithosphere and out into space. So the temperature flow. The temperature is so that the flow is always down the gradient, and here for the sill, the heat transport, and we see only the top really. We don't see the bottom. We see the top part of the sill is somewhere here. The consequence of the heat flow and shrinkage would be that these joints will start to form somewhere close to the top, and then propagate down into the center, And you see they're very, very regular here. Now, how long time did this take? Well, we don't know the exact thickness of this sill. It's obviously tens of meters. But let's say if it was 50 meter thick initially, how long time would it take it to solidify, just to solidify? That is to go from 1200 degrees to 1000, still very, very hot. It would take at least 45 years. 45 years. So these kind of bodies can be liquid for a long time. In fact, in some years ago, there was a drilling in northern Iceland where, as a great surprise, they drilled into a fluid sill that had been emplaced in 1729 and was still part of it, fluid. Now, ideally, the rock columns are hexagonal. Why? Well, here we are coming again to a minimum principle in physics. So as you may recall from some of my talks, I mentioned the principle of least action, controlling the propagation of dikes, which when time doesn't come into play, reduces to principle minimum work or minimum potential energy. So these minimum principles demand that the interior angle here would be 120 degrees, so that ideally they should be hexagonal. The total sum, of course, 720. Now you could say, well, to minimize, wouldn't circle be even better? Yes, from a minimum point of view, but then you would leave space in between the columns, which would not be allowed in this case. So the hexagonal structure is in fact the most efficient one. Now, when they cool down, this is the ideal situation, but there is crack interaction, variation in stresses, and so on. So you do not always reach hexagonal columns. In fact, Sigurður Þórarinsson, a famous Icelandic volcanologist, he, many years ago, with his students, measured the columns, not here, but not so far away, again in southern Iceland, in an area called Kirkjubergklaustur, where there's a famous church floor, also made of rock columns. And he and his students, they found out that 47% were hexagons, and 41% pentagons. The other shapes like squares and so on were with a much lower percentage, obviously. Now here on the left is the ceiling of a cave around the corner there of the mountain you saw some slides ago of Reynisfjara. The cave is called Hálsnefshellir, and I show here the ceiling of that cave, and you see by looking quickly here that most of these are presumably pentagons and hexagonal in shape. So hexagonal is quite common, but as I say, in the measurement of Sigurður Þórarinsson, they were not quite 50% of the shapes. I promised to show you the feeder dike to the lava flows in the mountain Reynisfjara. Here you see that. The dike is very interesting. I've outlined it with these broken yellow lines here. It is relatively irregular in shape, and that's quite common to see in hyaloclastite mountains. Of course, they seek the path of minimum energy, this famous principle of least action. And you see here in the lower part, it is quite inclined, but then close to the paleo surface, which was here. So this was the surface when the dike came through. It becomes basically vertical. Why? Because the stress situation demands that when a dike injection comes to the surface, it meets the surface at crudely 90 degrees at the right angle. And that's exactly what we see here. So this dike here is connected to this set of lava flows and was the feeder to them. Then in addition, we see the hyaloclastite host rock and then pillow breccia here at the bottom of the section. But the dike itself is quite irregular. You see here it tried to go somewhere else, failed, and then decided on this path at the end. So they try always to find the easiest path, the path that costs least energy. So before we leave, we should have a look at these famous sea rock pillars or sea stacks named Reynisfjara. I show only two of them here. I will show you when I go to the village of Vík on the other side of the mountain. I show you that there are more than two, in fact. They're up to 66 meters tall, and they are made of basalt. As always, there are some folk tales around these kind of rock structures, and in this case, as very often, it was supposed to be some trolls or giants that saw the light of day and didn't tolerate it, namely, were turned into a stone. Why they were not able to escape to the caves before dawn, I do not know, but there are several versions of the story that indicate what really happened. So let's move on. So here we have driven to the east side of Reynisfjara. So we were on this side just before, so here on the west side where we saw the rock columns and the sills and so on. And now we are on the east side, and you see the same sea stacks again here. You see there are at least 4 major peaks, and maybe more if you, depending on how you count them, there. So from Vik we drive east to, so Vik is located here. You will look at these sea stacks here. So we drive now a little bit into the Mýrdalssandur, the sandur plains of Mýrdalssandur here. And we look at these mountains, Hafursey, Hjörleifshöfði, and keep in mind that during eruptions in the caldera of Katla, the flood normally comes down here, and I'll show you crudely how it goes down to the sea. There are some indications, historical ones, that occasionally floods can come down here to the west and even somewhere else, but most of them would have gone down here, and that's usually what one assumes that will happen, and we would expect it in the next eruption in Katla. So Katla is a central volcano, a polygenetic volcano, and of course is a collapsed caldera. It's located in the ice cap of Mýrdalsjökull, which is large here. And when eruptions happen, the hot magma, 1200 to 1250 degrees, melts part of the ice cap, and that leads to floods that come down here from this glacier Katla, and then flow down here in all directions. Now, how often do we have eruptions in Katla? Historically, in the past 1100 years, on average, there have been an eruption twice per century. Now, the last one, a major one, was in 1918. So you could say eruptions are overdue. The eruptions are overdue. So people are ready for a new eruption. That is, in a way, we could say we expect a new eruption to come in the coming years. As I said, Katla is a collapsed caldera, and here is a schematic indication of the shallow magma chamber beneath the collapsed caldera. For a collapsed caldera to form, there must be a shallow magma chamber, and the chamber must have a plan view geometry similar to the plan view geometry of the caldera at the time when the caldera forms. We also show or in this illustration, they also show the little inferred magma chamber in Eyjafjallajökull, and you see the distance here is only around 25 kilometers. So you could expect some kind of a mechanical interaction between them. And historically, of course, there have been very few eruptions in Eyjafjallajökull, but historically, when eruptions happened in Eyjafjallajökull, usually they were followed by eruptions in Katla, but eruptions in Katla have been many more than Eyjafjallajökull. However, in 2010, in the last eruptions in Eyjafjallajökull, there were basically 2 eruptions there. First one outside the glacier, and then one through the glacier. No eruption, however, happened in Katla, at least so far, following the eruption in Eyjafjallajökull in 2010. So volcanology, volcanic tectonics can be complex, and it's often difficult to forecast what will happen, really. So where would the floods go? Well, I indicated here's a map from Guru Lassen and redrawn by Ari Trausti Guðmundsson, but I've added to it a very schematic indication of where the flood would go. In fact, it goes everywhere here, basically, but goes around the mountain Hjörleifshöfði and the mountain Hafursey. Also indicated here schematically are the old settlements. So when the Vikings came here 1100 years ago, there was vegetation here in this area. They were not sandur plains as we see today. So there were farms here. So these are the locations of known farms in the area, and they were not destroyed probably until after several hundred years. So the floods did not come very much down here in the early centuries after the settlement 1100 years ago. They went more to the east. But in the last, say, 500 years or so, or 600 years, they have gradually, the floods, destroyed the whole settlements in this area. I indicate, as I say, Hjörleifshöfði and Hafursey here, and Katla is located there, and this is the Katla glacier, this one here, shown here, from which most of the floods come down. So here are some of the features we saw on the last slide. View north, looking north. Here is Katla glacier. See the top of it here. Hafursey, the big mountain, is up to 580 meters above sea level. And even if it has the name Ey, which means island, it was definitely not an Ey or island when the Vikings came 1100 years ago. It may have been an island, of course, sometime during the end of the Ice Age or something like that. But as I say, these sandur plains were, during the early centuries after the settlement, were covered with vegetation. So there were people living here. There were farms here. But the floods were much smaller in the early part after the settlement, but they became gradually larger from the 15th century, and then began to destroy all these areas. And of course, there's no one living there now. So here is Hjörleifshöfði. It's a hyaloclastite mountain, not very large, reaches a height maximum 220 meters. Probably formed a submarine eruption, similar to this Pétursey we saw earlier. And this is famous in the history of Iceland because this is where one of the two main settlers came on land, Hjörleifur Hróðmarsson. He took land here, and therefore this is named, this cape is named after him as Hjörleifshöfði. Höfði means cape. But the floods of Katla have extended the coast, so there was a fjord here when Hjörleifur came here on the west side of it. So it was really extending into the sea, but now the coast has extended due to the floods some 3 kilometers to the south from the south end or south edge of Hjörleifshöfði. So how large are the floods during Katla eruptions? We have reasonable estimates of the last one, 1918. The maximum discharge there seemed to have reached somewhere between 200 and 300,000 cubic meters per second. That is enormous. That is enormous. Some people estimate that the largest eruptions in Katla may in fact generate maximum floods of up to 1 million cubic meters per second. 1 million cubic meters, but at least the facts as we have them indicate 200 to 300,000 cubic meters per second in the 1918 eruption and floods. For comparison, the largest river on Earth in terms of discharge is, of course, the famous Amazon. And its discharge on average is just over 200,000 cubic meters per second, 209. So there's a similarity here between the maximum discharge in the Katla eruptions and following floods and the largest river on Earth in terms of discharge, namely Amazon. What is the velocity? How quickly does the flood come down the sandur plains? It is estimated it goes by around 15 kilometers per hour. So commonly, just to remind you, a jogger runs maybe 12 kilometers per hour. A walking person, 4 to 5 kilometers per hour, something like that. So 50 kilometers per hour is the velocity. So if we are on the road number 1, the minimum time it would take for the flood to come from the glacier, Katla glacier, to the road would be around 1 hour. However, Katla is extremely well monitored, particularly by earthquake monitoring. And if there is indication of eruption, Road 1 in this part will definitely be closed. So well before any such eruption would happen, it is definitely, people will definitely decide to close it before any eruption would be likely, based, as I say, primarily on earthquakes. And with these words, while we look here again to Hafursey, and this gentleman here standing on road number 1, so one of the main part of the flood would come down here, this path here. By looking at it, I say simply, thank you very much indeed, and for now, bye-bye.